this video, we're going to talk about linear systems. So first thing let's do is we'll define a linear equation in R2. So that looks like ax plus by equals c, where a, b, and c are real numbers. So in other words, it's an equation with two variables, x and y, real number coefficients. A linear system is what you get if you put two of these equations together. So in theory, a linear system could have more variables or more equations, but in this video, we'll mostly focus on the situation of two equations in two variables. So the important thing to notice with these linear equations is that the variables always appear just to the first power. So you'll never see anything like an x squared or a 1 over y or root y or sine y or anything like that. It's just a real number times x plus a real number times y equals a real number. Imagine that we have two linear equations in R2. So each of those linear equations represent a line. In other words, we've got two lines in the xy plane. Those lines could be parallel. They could intersect at one specific point, or they could actually be the same line. So we've actually got two lines that lie right on top of each other like that. Now, when we're solving a system, what we're doing is we're looking for the intersection of the two lines. So in the first situation where the lines are parallel, the system would have no solution. In the second situation where the lines intersect in a single point, we would have one unique solution to the system. And in this third scenario where the lines are actually the same line, if you count how many points are common to the two lines, well, it would be infinitely many. Every single point along this common line would solve the system. So we'd have infinitely many solutions. So we're going to look at those three scenarios over a variety of examples. Now, a little bit of terminology here. If a system has no solution, then the system is called inconsistent or an inconsistent system. And anytime a system is solvable, whether it's got one unique solution or infinitely many solutions, it's called a consistent system. So when you see this word consistent, think of that as being solvable. It has one or more solutions. So we are going to solve this system by a process called elimination. And first thing we're going to do is we're going to write up this system in matrix form. So the first column is going to represent the x coefficients. Second column is going to represent y. This vertical bar that we're seeing here represents the equal signs. And then over on the right side, we have the constants. So we're going to take the first equation in the system and we're just going to pull out the coefficients. So they are 2, 6, and then negative 14. So we're translating that equation 2x plus 6y equals negative 14 into a more concise form, and it becomes this row of the matrix. So to build the matrix as a whole, what we're doing on the left side of the matrix is just pulling all the coefficients out of the system. So 2, 6, negative 3, 3. And then we've got our vertical bar to represent the equal signs, and then we're putting our constants on the right side. So that's the matrix form of the system of equations. Now the plan is to do some row operations, and we'll talk about those in a minute. We're going to perform some operations on this matrix, and the goal is to get something that looks like this on the left side of the system. We want ones along this main diagonal here, zeros everywhere else, and we'll have some numbers on the right side. So the reason that we're aiming for this is because if we then think about what this top equation reads as, if we put it back in the form of an equation, that would look like 1 times x plus 0 times y equals whatever number we have on the right side. So in other words, that's just allowing us to read off the value of x. And in a similar way, the bottom row is allowing us to read off the value of y. So let's talk about the row operations that we're allowed to perform on this matrix. So there are 3 elementary row operations. So these are the operations that we're allowed to perform on the matrix when we're trying to solve the system. We can swap 2 of the rows. So swap the top 2 rows, for example. We can multiply or divide any row by a non-zero number. And the third thing we can do is we can take the current row plus or minus a number times the pivot row. So this operation will probably become a bit more clear as we do an example. So let's bear in mind that what we're looking for is ones along the main diagonal and zeros everywhere else. And we'll talk about a specific process that's going to help us create this matrix. So first thing we're going to do is we're going to get a 1 in the upper left-hand corner. And that 1 is going to be called the pivot. We'll just give it a name because we're going to be referring to it later. The operation you want to think about when you're trying to create a 1 is just divide that row through by an appropriate number. So we're going to take row 1 divided by 2. So divide all the numbers in the top row by 2. We get 1, 3, -7. So that is like saying we have the equation 2x plus 6y equals -14. And we're allowed to divide both sides of an equation by 2. So we've just changed that equation by saying x plus 3y equals -7. So we've now got an equivalent equation. In the same way, all of the row operations that we perform on this matrix are just changing the way the system looks, but they're not changing the information that's encoded in the system. So we're progressively just going to make the system look better. By the end of the problem, we'll be able to read off the solution, but we have not changed the solution along the way. So we're just going to recopy our bottom row because that's not changing. And we'll keep this 1 circled because that's going to become important now. Once you've got a 1, then you want to get zeros in the rest of that column. And in this case, there's only one other number in that column, the -3. But in general, when we move into bigger systems, there may well be, say, 2 other numbers in that column. We'd like to turn them both into zeros. So we want to get rid of this -3. Let's think about the operation that's going to do that. So think about going current row plus or minus some number times your pivot row. So current row just represents whatever row the number is in that you're trying to eliminate. So the -3 is in row 2. We'll call that row 2. And then we're going to add on or subtract off some multiple of our pivot row being the row where the 1 is. So that's why we keep that 1 circled. Pivot row is row 1. Okay, so the correct operation to do would be row 2 plus 3 times row 1. You can just visualize here, if you went -3 plus 3 times 1, that would create 0. So that would just be the perfect operation to create a 0 here. And in general, if it's a -3 that you're trying to eliminate, you're going to be going plus 3 times your pivot row. If it were, say, a +7 that you were trying to eliminate, you go row 2 minus 7, row 1, etc. So we'll get lots of practice with that as we go through these examples. Okay, so for the bottom row, let's apply this operation of row 2 plus 3 row 1 all the way across. So we'd have -3 plus 3 is 0. We'd have 3 plus 3 times 3 is 12. And then on the right side, we'd have -15 plus 3 times -7 is -36. So that's our bottom row. So at this point, we've cleaned up the first column. We've done this pattern of getting a 1 and then getting zeros in the rest of that column. So we're now going to move over to column 2. So move from our previous pivot. Let's move down and right. We want this to be our new pivot. So our goal here is to get a 1. And the way that we accomplish that, just divide the row through by an appropriate number. So we're going to go row 2 over 12 to create that 1. That's going to give us 0, 1, -3. Top row is not changing at that point. So we can just recopy that. Okay, and we're going to circle that 1. That's going to be our pivot for the second column. And now our goal is to get zeros in column 2. Okay, and in this case, it's really only one number that needs to be turned into a 0. But in general, when we get into bigger examples, we might have more than one number in column 2 that needs to be eliminated. And so we think about doing all of those operations at the same time. Okay, for now, let's just focus on getting rid of that 3 in the top row. So let's think about anytime you're trying to get a 0, think about the pattern of going current row plus or minus some number times our pivot row. And the number that we're going to use is just the opposite sign of the number that we're trying to eliminate. So the correct operation would be row 1 minus 3, row 2. So row 1 is our current row, negative 3 is the sign change of what we're trying to eliminate, and row 2 is our pivot row. So let's try that. Row 1 minus 3, row 2 would give us 1 minus 3 times 0 is 1. 3 minus 3 times 1 is 0. And then on the right side, negative 7 minus 3 times negative 3 gives us 2. Okay, so we've accomplished that pattern that we were trying to create of having ones along the diagonal, zeros everywhere else, and we're now just able to read off the solution. See, the top row says 1 times x plus 0 times y equals 2, or if we wrote that in a more natural way, that's just saying x equals 2. Bottom equation, in a similar way, is giving us the value of y. So y equals negative 3. If you wrote it out the long way, it would look like 0x plus 1 times y equals negative 3. But more naturally, just y equals negative 3. And then we tend to write up our answer just in vector form because it's a more concise way of writing the answer. So xy is 2, negative 3. And you can check that that satisfies both of the equations that we started with. So the main thing to absorb from this example, I would say, is just the pattern of which operations you do when. So just think about this rhythm of getting a 1 and then getting zeros in the rest of that column. And then you get a 1 on the next diagonal position, and then you get zeros in the rest of that column. So that's going to start to feel very familiar as we go through several examples. So just a little bit of terminology now that we've seen how to set up these matrices. The name for the matrix that we set up when we were solving that system, that's called the Augmented Matrix. And if for some reason you just wanted to talk about the left side of that, you would call that the coefficient matrix. So now we have a system already written up as an augmented matrix, and we'd like to solve the system. So let's try the same sort of plan as we did in the previous example. First thing we're going to do is get a 1, which we're calling the pivot, in the upper left-hand corner. And the way you do that, just divide your row by an appropriate number. So let's go row 1 divided by 2. That would give us 1, negative 3 halves, and 4. And we will recopy the bottom row because nothing's changing there. I usually get in the habit of just circling the pivot. For some reason, it makes the next step a bit easier psychologically. So once you get that pivot, then you're going to get zeros in the rest of that column. And for us, that just means getting rid of this negative 4. So the operation that you're going to do anytime you're trying to get a 0, think about going current row plus or minus some number times your pivot row. And the plus or minus number that you're using is just the sign change of the number that you're trying to eliminate. So sometimes I think of this as current row minus k times the pivot row, where k is the number that we're trying to eliminate. That's another way of thinking about it. So that negative 4 is in row 2. It is a negative 4, so we need to go plus 4 times our pivot row. And that will exactly create a 0 for us. So negative 4 plus 4 times 1 gives us 0. 6 plus 4 times negative 3 halves gives us 0. And then over on the right side, 20 plus 4 times 4 gives us 36. So something strange has happened here, and I'm just going to write up the names of the variables so that we can talk about this bottom row of the matrix. So let's translate that into an equation. That says 0x plus 0y equals 36. And that is impossible. There are no x and y values out there that satisfy this equation. And so what that tells us is that the system as a whole has no solution. So the system is unsolvable. It's not possible to find a pair of real numbers x and y that satisfy both equations at the same time. So let's come up with a quick way to recognize this if we see this again. So if you see the pattern where you have all zeros in the coefficients and then you have something non-zero on the right side, then the system has no solution. So as soon as you see a row like this anywhere in your matrix, the process stops and you just say the system has no solution. So let's try another example of solving a system. Again, it's given to us in the form of an augmented matrix. So first thing we're going to do is get a 1 in the upper left. We're going to call that the pivot, just so that we can refer to that in later steps. So the operation that's going to do that will go row 1 over 2. So 1, negative 3/2, 4. So some of these numbers look familiar from the previous example, but we'll see there's a big difference in what happens as we go through the solution. So we just recopied that bottom row. Let's circle our pivot here. Once we've got that 1, then we're going to get zeros in the rest of that column. So the operation that's going to do that, think about going current row plus or minus some number times your pivot row. And if you want a different way of thinking about this, the actual plus or minus value that you need to use is just a sign change of whatever number you're trying to eliminate. So sometimes I think of this as current row minus k times the pivot row, where k is the number that we're trying to eliminate. All right, so we're getting lots of practice with that operation. So to get rid of this negative 4, then we're going to go row 2 plus 4 times row 1. So that's the row that we're on, and then sign change of the number that we're trying to eliminate times the pivot row. So negative 4 plus 4 times 1 gives us 0. 6 plus 4 times negative 3/2 gives us 0. And then now on the right side, we've also got 0. So that's as much as we can do in terms of the matrix row operations. See, we can't create a 1 in this position, at least not without destroying the structure of column 1. So dividing this bottom row through by something doesn't create a 1. Swapping rows will destroy the structure of column 1. And similarly, going something like current row plus or minus a multiple of the pivot row, that would also destroy the structure of column 1. So we've done as much as we can in terms of the row operations, and we just need to figure out how to solve the system. So let's talk intuition for what's happening before we actually solve the system. I'm going to put the names of the variables on here. So bottom row is saying that 0x plus 0y equals 0. And that is giving you no information. So that's telling us absolutely nothing about our x and y values. In other words, when we look at this matrix, we've really only got one solid piece of information, and that is coming from the top row. So what this means is that our system is going to have infinitely many solutions, because there's going to be some freedom in how to choose our variables. Okay, let's talk specifically about how we solve the system. So here are the general instructions. We are going to circle the leading non-zero entry in each row of the matrix. So let's do that. So in the top row, the first non-zero number that we run into is that guy. And in the second row, well, it's all zeros. So there are no non-zero entries to circle. Essentially, what this circle represents is the ability to solve for x. So because we've got a circle in the x column, that tells us we can solve for x. Second piece of information says any column without a circle is a free variable. So notice how the column for y does not have a circle in it. That means that y can be any real number. And the way we're going to encode that is we're just going to give y a new name. Typically we'll call it t or k or something like that. And that encodes the fact that y can take on any real number. See, if we just called it y without changing its name, it wouldn't be clear whether y is a number or whether it's a free variable. But by changing the name, you're really emphasizing that, okay, it can take on any real number value. So once we've decided that, we can then solve for x using the top equation. So top equation says that 1 times x minus 3/2 y equals 4. Let's solve that equation for x. So we'd say x equals 4 plus 3/2 y. And then just use the fact that y is equal to t to say x equals 4 plus 3/2 t. And that way we have our values for x and y in the language of t. So this number t here that we've introduced, if we ever want to refer to that, that's called a parameter. the parameter, or in some problems we'll actually have multiple parameters, so we'll say that's a parameter. And we'll talk more about that in some of our upcoming videos. So usually the most concise way to write up our answer then is in vector form. We're going to write something that looks like this. xy equals some vector plus t times some vector. And so geometrically what this represents is a line, because based on our geometry discussion before, we said if you have two equations that really represent the same line, and we're talking about two lines in the xy plane, then when you go and solve that system, you're going to get infinitely many solutions because every point along that common line solves the system. So if we write that line in vector form, it's going to look like this. So let's figure out how to make this shift to get this actually into vector form. So let's look at the x first. X is equal to 4 plus 3/2 t, so we would go 4 plus t times 3/2. And then y is equal to t. So rather than saying y equal t, you could think of that as y equals 0 plus 1 times t, and that would help you fill in your numbers. So y is the number 0 plus 1 times t. And that's usually the most concise way of writing down our answer. So most important takeaway here is that the system has infinitely many solutions. For any real number t, you can plug t in and get one specific combination of x and y values that work. And as you range over all the possible t values, you're tracing out all the different points x, y that solve that system. Right, so here we've got another augmented matrix for a system, and let's go through and get a bit more practice with solving. So first thing we'd like to do is create a 1 in the upper left, and that's already done for us. So our next job is to get zeros in the rest of column 1. In other words, we want to get rid of the 2 and the 3. And we can do both of those operations at the same time. So the rule is we're going current row plus or minus some number times our pivot row. And if you prefer to think about that number specifically, it's just a sign change of the number that you're trying to eliminate. So you could say it's current row minus k times pivot row, where k is the number you're trying to eliminate, if you find that easier. Okay, so we go row 2 minus 2 row 1, and at the same time, row 3 minus 3 row 1. So in each case, we're talking about the row that we're on, sign change of the number that we're trying to eliminate times our pivot row. Pivot row is row 1 because that's where our 1 is sitting. Okay, and top row will not be changing, so I'll just write that down. All right, so row 2 minus 2 row 1, that's going to give us 0, 3, negative 6. Row 3 minus 3 row 1 is going to give us 0, 4, negative 8. And so now the first column is cleaned up. We got our 1 and then we got zeros all the way through the rest of that column. Okay, now our goal is still to try to create something that looks as much as possible like this structure. We don't really know exactly what's going to happen in the bottom row yet, but let's just look ahead and realize that we're going to want this 3 to become our pivot for the next step. We want our 1s to move as diagonally as possible. So on the step when you're trying to get a 1, you're typically just dividing your row through by a certain number, so row 2 over 3. Okay, so row 2 over 3 looks like 0, 1, negative 2, and the other 2 rows are not going to change at this point, so we will just recopy those. Can circle our 1, and then we're going to use that pivot to create zeros in the rest of that second column. Well, in the top position here, we've already got a 0. So it's just a matter of going row 3 minus 4, row 2. So again, the row that you're on, sign change of the number that you're trying to eliminate times your pivot row. So that's going to look like 0, 0, 0 for the bottom row. We have made this matrix as nice as possible. We've gotten the pivot in each column. We've gotten zeros in the rest of those columns. So we're actually ready to solve the system. So let's write up the names of the variables. So the most foolproof way to solve a system is to just go through the rows of the matrix, go through row by row, and circle the first non-zero entry that you see. So in the first row, it's there. In the second row, it's here. The bottom row doesn't have any circles. Each circle represents your ability to solve for that variable. So this circle here says that we can solve for x, and this circle here means that we can solve for y. So that tells us that our system has a unique solution. There's just one combination of x and y values that work. The bottom row, interestingly, contains no information. And the reason why that's true is because our system actually started off with 3 equations. So one of those equations was redundant or just not helpful right from the beginning. We just didn't need it. We only really needed 2 equations to be able to solve the system. So the third one was just extra, and by the time we had done all the simplification, that third equation just reduces to no information. All right, so let's see if we can solve our system. Top row says that 1 times x plus 0 times y equals 5. Well, if we write that more naturally, that's just saying x equals 5. And second equation, if we write that more naturally, y equals -2. So you could write it like this, although in the course pack, you're typically going to see them writing it in vector form where they just encode their solution like that. So we're going to solve this solve this system by a process called back substitution. This is something that we're going to be using in our next section. So it's essentially just a little preview to get us organized for that next section when we're dealing with bigger systems of equations. So this process of back substitution, that means just start at the bottom of the matrix. So you notice that at the bottom of the matrix, we actually have a relatively simple equation. It says 0x plus 0y plus 2z equals 8. And if we just don't write down the 0 terms, that's just really saying 2z equals 8. So that's something that we can solve relatively quickly and get our z value. And then what we're going to do is just sequentially work our way up the matrix. So now look at the middle row. That says 3y plus 5z equals 29, but we know the value of z. So plug in your known value. You can say 3y plus 20 equals 29, and then you're able to solve. So that reduces to 3y equals 9. In other words, y equals 3. So now, looking up at the top equation, that says 4x plus y plus z equals 15. The idea is now you can use both of your known values. So we know z is 4, we know y is 3. Let's plug those both in. So we'd have 4x plus, 3 plus 4 is going to give us 7. So 4x plus 7 equals 15. And now that's pretty easy to solve. So 4x equals 8, meaning x equals 2. Okay, and then if we wanted to write our answer in vector form, we would just write vector x, y, z equals 2, 3, 4. So that process of starting at the bottom is called back substitution, and we'll just store that idea away and we will be using it in our next section. So that's our intro to solving systems of equations. Our next section is going to contain more detail and more examples about all of these processes. Thanks for watching.